I'm very happy to be here. It's my first live event since a long time, so I'm very happy to be there, and especially with you, students, PhD students. It's really a pleasure. So I've been given the task of talking about nucleosynthesis in the universe, and you will have to bear with me for 3 hours. I hope you will be happy and you will like it. It's not easy to cover the entire topic, even in 3 hours. And I have selected a few things, and I also tried to make the link between chemistry, physics and astrophysics. And I know some of you know much better than me in some of these fields, so don't be shy to speak and to say, oh, this is wrong or this is not precise enough. Okay, I'm not susceptible. Actually, I'm here to learn as you are. Okay. So maybe I must say who I am a little bit, or because you introduced yourself yesterday, so maybe that could be useful. So I'm a professor at the astronomy department of the University of Geneva. Which is famous because that's where Michel Mayor and Didier Queloz actually discovered. That's not where they discovered, but they were from here. It's famous for many other things, actually, also nucleosynthesis and galaxy evolution and things like that. But I guess most of you know the exoplanetary people there. I'm also a senior researcher at CNRS in Toulouse. I'm on leave in Geneva now. And I did my studies in Toulouse at what was not yet IRAP, but at the Observatoire Midi-Pyrénées. I did my thesis on the production of lithium in the universe and the destruction of lithium in stars. And then I went for a postdoc at Geneva University and came back to France, where I got my CNRS position. And I traveled around. I spent some time in Baltimore at the Space Telescope Science Institute. We were discussing about that this morning. It's the amazing institute of the Hubble Space Telescope and now the James Webb Space Telescope. And I've spent some time also in other places, Seattle at the Institute for Nuclear Theory and other places. And actually, I think it was the first astrobiology school, so not the form it has now, but the one in Corsica. As a student, actually, it was a long time ago. I think I was still a student, or maybe I had my position already. So it's a pleasure. It's a pleasure to be here long time after that to give a lecture there. My task is to tell you about where these elements form, the chemical elements that you see here in this periodic table. And I've chosen this one just on purpose, like if I was giving a lecture in front of people studying economics. And you see the description actually in the table, you see where the elements are used for. But you are not studying economics, you are studying science, and I guess that maybe for you it speaks a little bit more where the ordinary matter comes from and not so much about how we can use it here on Earth. So I'm going to discuss the origin of these elements, and what is extremely fantastic is to think that all the elements that you find in this beautiful tree, or that you find in minerals, in the baby eyes, or in bacteria, or in the universe, in these large-scale globular clusters, or in galaxies, they actually formed the same way. And we are all made of the same ordinary baryonic matter, which is described here in these tables. You probably all know that, but it's very important to remember that we are made of the same material, which was formed in the early universe and also in stars, as we will see. So before starting, because I'm a little bit lazy person, if you have the possibility to screen this QR code with and if it doesn't work, I will circulate the paper version. I would be very happy if you could take a few minutes, maybe do it by 2 or individually. If you could take a few minutes just to answer to the few questions that I have asked in this questionnaire. Okay, so this is the plan of my lectures. As I said, I will briefly scan a few points about chemistry, astrophysics, and nuclear physics. Then I will talk about the stellar factories of the chemical elements. We'll give you a little bit of basics of chemical evolution. And then, if I have time, I will talk about the special case of helium-3, which will lead us to the moon, as you will see. A little bit of history, actually. In the ancient time, in antiquity, there were already some elements called metals that were known. They are listed here, and all of them were actually linked to one object of the solar system. Gold was, of course, related to the sun, silver to the moon, and you see the other elements were related, for example, iron to Mercury, etc. So there was already some connections between the metals on Earth and the space. Of course, the connections are very different now, as we will see, but it was already a sign that astronomy and physics and chemistry were linked together. At that time, also in the ancient Greece, the concept of atoms was already set by Democritus and Leucippus, who actually looked at water, for example, and saw that you can actually recover the same water even if it has been frozen or if it has been evaporated. So that gave the concept that there was an element which was below this water, actually, which was the link between the three different phases. And then that concept was lost for some time, also due to the Greeks like Thales and Aristotle, who actually suggested that there were actually 4 fluids, or called elements, which were underneath every material, and they call that earth, air, fire, water, and ether for what was going out, for what was outside the Earth, actually in space, in the sky. And I said it was lost for some time, even though in the mid-eastern part of the world, there were actually people working on what was called alchemia, which is the Egyptian art for alchemy. And you see also in these graphics that actually these people, they were investigating how you can transform matter, but they were also working a lot on astronomy. So everything was linked. And there is actually a crater on the moon that has the name of this person who was a chemist and an astronomer at that time. This concept of atom was kind of lost, and when in Europe, actually, people started to do science in the 18th century and starting to discover what was called element at that time, even though the people didn't know what that meant, an element, actually, they could isolate some elements from some gases, for example. We started to have a list of individual elements that were discovered by different techniques. And that led to the renewal of this concept of atomic theory by Dalton, actually, who thought that there was, beneath each of these elements, there was only one atom, actually, a sphere, an atom, which was at the base of the elements. And then the discovery of these elements went on through different techniques, the advent of the electrolysis and also of spectroscopy allowed to find different elements, to individualize them. If you want actually to do that yourself, you can practice. I found a very nice place on the web where you can do all this chemistry stuff. I guess for most of you it's very easy and you have done that in your studies. But if you want to practice a little bit, you can have a look at this and do it yourself in your own laboratory or in your own kitchen. So that led to the end of the 19th century to this periodic table. Here you have a written periodic table written by Mendeleïev, actually, which wrote this essai d'un système des éléments selon leur poids atomique et fonction chimique. So it was basically putting the tables in the elements in a system that was actually reproducing or interpreting their chemical properties. But it was at a time where we didn't know yet how these atoms were formed, and it was actually 8 years before the discovery of the electron itself, and almost 40 years before the discovery of the nucleus, the positively charged nucleus. So it's really interesting to see that at that time you could do some chemistry and find some properties that you didn't know what they were related to. I would say this is the way science is doing. Actually, you find things and then you interpret later, but I think it's very, very interesting. And that was really the start of a very interesting century. The 20th century actually was extremely interesting, because then you had to discover all these things below what was called the elements. So as I said, there was a process to understand the atom itself. So we started with this marble idea of Dalton here. I'm a little bit embarrassed with it. Okay, so you have this sphere, or this marble piece, which was called the element. And then later on, so after the discovery of radioactivity, there was this idea that actually an element might also not be stable, that you can have an element splitted apart itself. And then there was a discovery of the electron by Thomson at the end of the 19th century. So that gave this idea of not a marble sphere anymore, but of a pudding, where you will have negative and positive particles that would be in this kind of pudding called the element. And then it took some years still to discover the nucleus, which was concentrating the positive charge that was made by Rutherford and Geiger and Marson. And the Nobel Prize also was given to Rutherford in chemistry for this. And then Rutherford proposed this idea of a nuclear element, where you would have a positive charge in the middle and the electrons going around. Of course, this concept evolved with quantum physics. And for what is important for this lecture is that the neutron actually was discovered even much later, in 1931, by Chadwick, who also got the Nobel Prize in physics. And then later on there was the discovery of the artificial radioactivity. So I think it's important to remember this succession of events actually, and to see how long it takes to understand, how long it took to understand the element itself and the nuclei and its content. Then the physicists, they were actually also looking at the properties of these nuclei, and they found out that actually the mass of a nucleus is actually lower than the mass of the separated neutrons that compose this nucleus. This is what is called this mass defect, which is here, and it was related through the Einstein theory to what is called the binding energy, which is given here. So you have this mass defect here, and this binding energy is the energy which is required if you want to disassemble the nucleus into its constituent, but it's also the energy that was released when the nucleus formed through fission. And we will use this concept a little bit later in the lecture. So here you have this binding energy, which is plotted here as this is the binding energy per nucleon. So you divide this quantity by the mass number. And you see something which is very interesting, and that you certainly know also, is that when you go to heavier elements, you go to more and more stable elements. And you have some peaks in this binding energy, for example, carbon and oxygen, which are the multiples of alpha. And what is also very important for this lecture is that the most stable nuclei, they are actually around iron. So it's iron and the iron group elements. And all these elements, as you will see, they can be formed by fission. While when you go to heavier elements, actually, these reactions are exothermic and endothermic, and you cannot form these elements through fusion. So this is also something very important to remember when we will go to the formation of these very heavy elements. So this binding energy was extremely important, as I said, for the concepts of physics in general at that time, and it gave to Hans Bethe the idea that maybe in stars you could fuse hydrogen into helium, and you could get a lot of energy through this. So this is what you can see here. So you have 2 protons actually which are going to give deuterium and then capture another proton to make helium-3. And with 2 helium-3 you will make an helium-4. We will come back to that too. But what is important, if you take the mass of 4 protons and the mass of the nuclei, you have this mass defect here, and you see the energy release. So each time you produce an helium from 4 protons, this is the amount of energy that you get. So it was very interesting, but it was also understood at that time, because of the nuclear repulsion forces, that you would need a very high temperature to make this particle fuse. And it was estimated by Hans Bethe that this temperature must be of the order of 15 million Kelvin. So again, if you want to practice, but with nuclear physics it's a little bit more embarrassing. If you want to practice, you can go to this place here, and I'm showing you here. This was a toy that was actually sold. You had some radioactive elements and an electron chamber, etc., and you could do it yourself. So going back to chemistry, actually, it was also understood that if you hit matter, actually, and you put a diffraction grating here, you could get this very nice continuum, this very nice arc-en-ciel from light. And actually, it was also understood that if you have the hot gas here going, you can have actually some emission of photons due to the changes of the between bond levels by the electrons here. So you could get the emission, and doing that, you could have actually identify the chemical elements with their spectral signature. And then if you were doing the same thing, but with the light going through a cold gas, you would get, so the same gas as here, you would get actually the absorption spectrum, where the photons are actually captured at different energy levels related to the composition of the gas itself. So you have this absorption. And if you are able at the laboratory to make this emission and compare to what you see in nature, or maybe you see in stars, actually, you are able to identify the chemical elements which are actually composing the gas. So in the case of stars, and that was used very early by Fraunhofer at the end of the 19th century, the idea is that if the star actually is very hot and emits a spectrum in the interior, when this continuous spectrum is going through the cooler atmosphere, the chemical elements of the cooler atmosphere, depending on the composition, they will actually capture some photons at specific wavelengths, and you would then get this absorption spectrum. So this was used very early, actually, to try to figure out if the stars were made out of the same material than the material that we find on Earth. And of course, as astronomers, this is the only way we have to understand the composition of stars, except if you have some meteorites or some material that you can. But for the stars themselves, this is the technique that we have to use, of course. This technique was used to look at the sun, as I said very early on. And so this is one of the questions. Where was the helium discovered first? Was it in stars or was it on Earth? Helium comes from Helios. So it was Janssen and Lockyer who independently looked at the sun during a solar eclipse, and they found a line which was unknown at the laboratory, and this line they call it helium because it was discovered in the sun. And it's only a few years later that actually this helium was isolated in uranium-based minerals, and even later in an oil well. So the geologues and the chemists can tell me if it's wrong or if it's not precise enough. And as you know, actually, this element is very rare on Earth. It comes from the disintegration of radioactive minerals, and you can extract it from different minerals. So it's very rare on Earth, but it's actually the second most abundant element in the universe. It was created at the beginning of the evolution of the universe, as we will see, but it's the second most abundant in the universe. So using the spectrum, here you have the Fraunhofer line, actually. So this is a solar spectrum. You can actually look at these lines like that, and you can determine the abundances of the elements, but you can also determine a lot of things about the star, depending on the broadening of the lines. You can find if the star is a dwarf or if it's a giant star, if it rotates. If you have some splitting, you can also determine the magnetic field. If you have some emission lines, you can determine the mass loss. And if you look at, for example, galaxies, you can determine their redshift and how far they are from the observer. So this is a technique which is, of course, extremely important for astronomy. But actually, it's usually people say you have theoreticians and observers. These are not different worlds, actually, because the observers who look at these lines and who then determine the abundances, they have to go through very complex models. And here you have a schematic view of a model of the atmosphere that you have to go through to put on top of your data to determine actually all the properties that I mentioned before. So when you get an abundance of an element from a star, it's never the actual measurement. It's really an interpretation on what is in the spectrum through this model atmosphere, which is extremely complex because the atmosphere of stars are extremely complex. So out of this, we can find what is the actual solar composition. And here you see that on the left, you have the hydrogen, which is the 75% in mass in the sun, and helium is almost 25%. And the rest is actually 0.1%. You have the others. So what the astronomers call others, these are metals. Everything which is heavier than hydrogen and helium, we call metals. And these metals, you can see here, splitted on the right, the relative mass fraction of these metals within the sun. And so you see that actually oxygen is the most abundant of these metals. Then you have neon, carbon, neon, nitrogen, and you see that iron actually is a very modest abundance. There is another way to determine the composition of the sun, is to look at the solar vibration. So this is a technique of asteroseismology. You have the sun has a convective envelope, which is actually throwing waves within its interior. And when you look at the sun in photometry, you see some light variations that you can interpret as a result of these waves going through the star, actually. And through that, you can know to which depth the waves of different lengths go, and you can deduce the density and also the composition of the interior of the star. And through asteroseismology, we can determine, so in the sun, that the helium mass fraction in the solar envelope is around this value. So it's another way, extremely powerful way to determine the composition also of stars. In the sun, it's very easy because the helioseismology is easier to do. In other stars, it's a little bit more complicated, but it's an additional tool to do these kind of things. Another way to determine the composition of the sun, and we will hear later this afternoon, much more than I know and that I can say this morning, is to look at the meteorites. So as I said, for the solar photosphere, you go through spectroscopy, and it's strongly model dependent, so dependent on the model of your atmosphere. And in the case of meteorites, it's much more accurate through mass spectroscopy, and you can actually determine the abundances. The problem is that, of course, there are some noble gas and highly volatile gas which actually are depleted in the meteorites. But as you can see here in this plot, which compares the meteoritic abundances to the photospheric abundances, so it's in logarithmic scale, you see that apart from these elements, actually, there is an extremely good agreement over almost 10 orders of magnitude between the abundances that we determine, that people determine in the meteorites, and the abundances that we determine in the sun, in the photosphere of the sun. There is another element which is different. So in the meteorites, actually, it's more than 2 orders of magnitude higher in the meteorites. This is lithium. Lithium is an extremely fragile element which burns at quite low temperature, around 2.5 million K. So the sun formed with this, with the meteoritic abundance, actually, but later on during its evolution, there was some depletion of lithium in the atmosphere, which led to this composition. And this lithium is extremely important to understand how the magnetohydrodynamics of the sun, because we need to transport this lithium from the envelope down to the interior, and this is really an element which is a strong constraint to this transport mechanism inside stars. So what we can get from that is that actually the protosolar nebula, the protosolar cloud, was very well mixed. So these are the patterns that the most recent abundances that were published last year. So these are the photospheric abundances, and you see, interestingly, some patterns in these abundances. So you see, this is the abundances. They are here in logarithmic abundance, where you take hydrogen equal to 12. So this is the reference element here, hydrogen equal to 12. And then when you go to the other elements, you can see the variation in the logarithmic scale. So you see again that hydrogen and helium are the most abundant ones. Lithium is strongly depleted. We have also beryllium and boron, which are quite low abundances. And then you see these very interesting patterns where you recognize carbon, oxygen, neon, magnesium, and maybe you already count that these are a multiple of alpha. And as we will see in a minute, this is directly related to the nucleus property of the elements. What you see also is that iron stands outside these iron group element, and when you go to heavier and heavier elements, the abundance become really, really minute and decrease by orders of magnitude. So you remember this binding energy per nucleon curve that we had at the beginning, where we could see these peaks here. And this is a plot that was made by Nikos Prantzos, where you can, on top, look at these cosmic abundances, so in the sun, and you see that actually locally, the cosmic abundances, so the abundances on the sun, they are actually related to the stability of the elements. It's directly related to the nuclear binding energy of the elements. And here you see the different alpha elements, also magic numbers, etc. So it was understood already in the 40s, by comparison of these kind of curves, that the cosmic abundance, they were actually shaped by some nuclear processes, just by comparing these two curves. And as I said, it was established in the mid-40s, almost 1 century ago. And we tried to figure out where we can make these elements through nuclear reactions. So we knew from better that if you want to have some nuclear fusions, you need to have very high temperature. And at that time, there was a strong debate between two schools, those who thought that you could make all the elements in the Big Bang. So remember, Big Bang is, of course, only a theory. And we are here 30 years after the discovery of the redshift. So the fact that when you observe galaxies, the farther away they are, the faster they actually go away from you. And this gave rise to this Big Bang theory of the expansion of the universe, actually, that at some time the universe was much more compact, hotter, denser, and there was this idea by Gamow and other people that at that time, where the universe was extremely hot and dense, you can actually produce the elements, all at that time. And then there was another school, led by Hoyle, who proposed that actually the elements, they were made in the core of stars by thermonuclear reactions. And these people were actually really fighting to defend both theory. And then, of course, as usual, they needed some observational evidence. So at that time, there were observations of globular clusters. So here you have a sketch of our galaxy, and the small points that you have here, these are globular clusters. So these are very old clusters of stars, almost as old as the galaxy, 10, 13 gigayear. And in these clusters, we found some stars that had actually much less metals than the Sun. And we found also in the halo of the galaxy. When I say we, of course, it's the astronomers. They found some very metal-poor stars with very little metals. So this was embarrassing because that meant that if you had formed the metals in the Big Bang and then you see stars that have different abundances, that was really a plus for the stellar nucleosynthesis. And then there was another evidence which was really the clue for this. It was a discovery by Merrill in a giant star of technetium, which is an element that you find that has no stable form. It has a lifetime, I don't remember exactly the lifetime, but the point is that if you were finding this element in a star, and if you could age date this star, which at that time they had some ways to age date the stars, you were finding that the star was much older than the lifetime of this element. So that meant that if you could see the technetium in this star, then the star had to produce it itself. It had to be produced in situ. So these two points, these two observations, gave rise to a new field which was called the nucleosynthesis. And there was this seminal paper which I encourage all of you to look at. It was written in the 50s and which describe actually all the ways you can have to form stars, to form elements through nuclear reactions in stars. Both Gamow and Hoyle were right, actually. Why? Because Gamow, it depends if you take the mass of the elements, actually. Hydrogen and helium, they are the most abundant. So you could say everything was formed in the Big Bang. Okay? And the rest, these are the metals. So if you count in terms of the number of elements, then Hoyle was right, because you produce many more elements. But in terms of mass, actually, that was Gamow who was right. Okay, so stellar factories. I will go through very basic ideas about stars. This is the Sun. But you probably know that stars, along their life, they evolve and go through very, very interesting phases. And they undergo very, very interesting processes. We will go through these processes later on, but I already wanted you to enjoy these beautiful pictures of stars at different phases of their evolution. Also, the stars, we know that they are formed in giant molecular clouds, and most of the time they are formed in groups. You don't form a star alone, you actually form stars in clusters. And we see these clusters actually evolving and sometimes dissolving. Here you have the Arches cluster, which is a large number of very massive stars. So my first question to you would be, why do stars shine? And don't be shy to tell me, why does a star shine? Come on.
Nuclear synthesis inside of it?
Nuclear synthesis, another idea. So you're right, partly. It's like Gamow and Hoyle.
Yes, it makes a lot of energy that makes
Yes, yes. So this is the reason why stars shine for a long time. But it's not the reason why they are shining.
They're hot.
They are hot, yes. They are hot. You see? So it's the time where I present you my family, actually. And you see, actually, well, you probably have gone through these things over the two past years, you know, to get your temperature like this. So this is because they are hot, indeed. So here you have the spectrum of the sun. So this is the energy flux that you have per unit of time and per unit of surface as a function of the wavelengths. And you immediately recognize that, so the spectrum is in black, and you immediately recognize this the black body spectrum of the sun. And you know the Stefan Boltzmann, Wien's law, etc., which gives you the temperature of this black body through different waves. And if you want to determine the total energy flux of your star, you're going to integrate, and you will get this relationship with the effective temperature, TF, which is actually the temperature of the photosphere of your star, not the interior, but of the photosphere of the star, the layer where the photons escape. And to get the luminosity, the total luminosity, you have to integrate over the entire radius of the entire surface of the sun. So this is how we can get the luminosity and the effective temperature together. So you see actually that the hotter the surface, the higher the luminosity. So of course, you know that depending on your temperature, you're going to shine at different wavelengths. This is shown here. And so here you will have, if you go to a very massive star, which has a surface temperature of this order, 15,000 K, this star will actually emit most in the UV. But if you go to a cool star, it will emit more in the infrared. Okay? And here you have the spectrum of the sun. Here you have Vega, for example, where you have very specific lines. And here you have a very cool M-type star, which emits most in the infrared. And here humans, we emit at this wavelength, roughly. So, but then why are the stars hot? And it's not the same reason why we humans are hot, actually. Except maybe at the end of your life where you start. Well, they are hot because they are just a sphere of gas. This gas is actually condensed because of gravity. So I'm a ball of gas confined by gravity, and what is this gas going to do? It tries to contract, okay? So if you have only gravity and pressure, so the pressure is going to counteract this gravity. And here you have this equation, which is the second equation of stellar structure. So you see the astrophysicists, they have very simple equations. And it tells you that actually, under the effect of gravity, the star is actually contracting, and you have the pressure that counterbalances that. And you see the stars, they are very stable, except at the very last phases, actually, but they are very stable. The sun is not changing that much. Of course, there are nuclear reactions, so it's a little bit different. But you see that you can shine just because you are a ball of gas contracting. Okay? And with this very simple equation, you can actually find the pressure at the center of the sun. And you can also, if you take an equation of state, perfect gas, you can determine like this, the temperature at the center of the sun, and you will find something of the order of 20 million K. So if you do the exercise, find again these different equations, and you can, by knowing the mass and the radius of the sun, you can determine the temperature at the center. Pretty easy. This is what they have done, actually, better and Hall. Okay? So in the sun, actually, the temperature is of the order of 15 million K. So by this very rough exercise, you can find the right order of magnitude. Okay, so the star is in a hydrostatic equilibrium, and of course, if there is a gradient of pressure, there will be also a gradient of temperature. And if you have a gradient of temperature, the particles inside the star will actually, and in particular the photons, they will actually move through diffusive processes. It will take quite some time, but then you can actually transport the photons from the center to the outside with this very simple diffusion equation. The star shines because it's hot, and also especially because it's hot, you have a gradient of temperature inside which is imposed by the gravity. Okay? And what is very interesting, actually, and very important, is that you can find that the luminosity of the star, through these very simple equations, is proportional to the mass with this exponent here, 3.5. And you don't need to do that. You don't need to have any assumption about nuclear reactions. You can find this relation by observation. So here you have actually the luminosity of different stars as a function of mass. And here in this case, these are stars that were in binaries. So it's easier to determine the mass of the star in binaries. And also we knew the distance through parallax, precise parallaxes. So here you see the error bars are quite small, and you find this beautiful correlation between luminosity and mass. So if you remember only one thing out of my lecture is that mass matters. Okay? The hotter you are, the brightest you are. But if you compare actually the sun, so this is the power of the sun, and it's what you actually, the 100 watt is what you actually, your own power. If you eat, for example, 25 apples a day, etc., this is the comparison with the calories. And then if you compare the mass, this is the mass of the sun, this is the mass, rough mass of humans, and then if you compare actually the luminosity per mass, we are extremely more powerful than stars after all. It can shine just because of gravity, but how long can it shine through gravity? So if you want to determine how long it will last, you can use this virial theorem and find that actually half of the energy which is liberated by contraction, the gravitational energy, will be used to heat the star. So when the star contracts, the gas becomes hotter. And half of this gravitational energy is radiated away. So in the case of an ideal gas, you have this relationship between the luminosity, the internal energy, and the gravitational energy. And the time you can shine with only this contraction is given here. So it's the internal energy divided by luminosity, or the epsilon grav divided by 2L, because you have the 2 here. And you get this quantity, which gives you, for the case of the sun, this value of 15 million years. Okay? So if you are just contracting like that, the sun can last for 15 million years. If I turn off the nuclear reactions, it will stay like it is now for 15 million years. Okay, but of course, if you want the stars to shine for longer, you need an additional energy source, and this is where you were right, actually. Okay, so now if you compare this Kelvin quantity, which was actually determined at the end of the 19th century, this age, you all know actually better than me that there were ways also to determine the age of the Earth. And actually, Kelvin also computed this value, but he was wrong because it didn't account for the radioactivity, and for other reasons also. I think he didn't use convection in his model of the Earth, etc. But at that time, it was okay to find these two quantities like that, because it was okay with the Laplace hypothesis that the protosolar nebula and the Earth, actually, they formed at the same time. So these quantities agreed, but it was by pure wrong coincidence that they were agreeing. And of course, this was very early on in conflict with geology and with Darwin observations. And it's thanks to radioactivity that things could be put together. So radioactivity also gave this idea of this additional heat source inside the Earth, and it was used also to age date the meteorites and to find this age of 4.5 gigayear for the Sun, and also for the meteorites. By the way, this is the only star for which we know the age, actually. The Sun is the only star for which we know the age. So when we derive the ages of stars, we go through models which are extremely complicated, because there is a lot of hydrodynamics, nuclear stuff, etc. So we do these models, and then we say, out of what we know from the sun, we extrapolate with our models to determine the age of other stars. So this agrees pretty well with the age of the oldest rocks on Earth, and it's also agreeing very well with the age of the moon. So if we want the stars to last longer, we need to have this other thing that Bethe proposed, so this hydrogen burning to helium. And in order to compute this, you can get the nuclear energy that you will actually get from the Einstein equation here. And here you need to know what fraction of the star you're going to fuse. So in the case because you have this very strong gradient of temperature, the nuclear reactions, they actually occur only in the core of the sun and not everywhere. So you are going to burn something like 10% of the hydrogen in the core. And here you get the amount of energy that you get for one fusion. And at the end of the day, if you compute, you get this nuclear timescale, which is actually proportional to the mass and inversely proportional to the luminosity of the star. And if you actually remember this relationship, you get that the lifetime of a star, through which is actually burning hydrogen into helium, and you will see this is the longest phase of nucleosynthesis in stars. You get this quantity for the sun, so roughly 10 gigayear, meaning that the sun is at the mid of its life. But you see that it's a little bit counterintuitive, but the more massive the star, the shorter its lifetime, okay? Just because it's so luminous that it has to compensate this gravity, and to do that it has the nuclear phases have to accelerate inside. And actually you see that for a star which has 1/10 of the mass of the sun, it lasts much longer than the age of the universe. And if you look at a 60 solar mass star, it lasts only 3 million years. Okay, so here again, mass matters. The more massive you are, the faster you're going to die if you are a star. So I'm going to compare a couple of lifetimes. So I spoke about the Kelvin, Helmholtz, the nuclear lifetime, and now I'm just going to mention the freefall time. So imagine at the time you don't have nuclear reactions, and you have no more way to compensate the gravity. So you remove the pressure. You have this freefall time, which is given by this expression here. And you get that if you remove nuclear reactions, if you remove the pressure, your star is going to collapse very quickly. Okay, so it's not going to happen in the sun, but in some stars you have this freefall timescale, which is going to be important. So if you remember this timescale, the longest timescale is this nuclear timescale, much longer than the Kelvin-Helmholtz, which is also much longer than the freefall timescale. And what is important is that actually the luminosity of the star doesn't adjust to the nuclear reaction. It's the opposite. So because the star has a mass, it has a gradient of temperature, a certain temperature inside, and then the nuclear reactions will adjust to that. Okay, so what about now the interior? So we spoke about the sun, the temperature inside the sun, and here in this plot you have the temperatures in logarithm at the center of stars. So these are models, stellar evolution models, where you see the temperature, the central temperature versus the central density. And each of these lines here is the evolution of these quantities inside a model of stars of different masses. So you have 0.8, 1, 1.35, up to 120 solar masses. Okay? So we go from the low mass stars to the massive stars here. And you see that the more massive the star, so the beginning is here of the evolution. And you see that the more massive the star, the hottest and the densest the core is. So the stars, they will move like this because the core is actually always contracting a little bit. So you will actually move to this direction where you will see the density and the temperature increasing all along the evolution of the stars. And here, during this phase, here you will burn hydrogen. Then there will be no hydrogen anymore. The star will contract, zoops, go to helium burning, and then zoops, go to carbon burning, eventually, if you are a massive star. Okay, if you are a massive star, you go through all these phases of nucleosynthesis that I will detail later. But you see that the more massive you are, the further you can go. Now, if you are a low mass star, you have a problem. Because at the end of the evolution, you see that you enter this this region, which is actually the region. What I forgot to say is that here, in the case of massive stars, you can always consider that you have an ideal gas. But when you go to the low mass stars, at some point, you will have the degeneracy, electronic degeneracy that will happen. So in this case, you will have, when the core contracts, you will have these poor electrons that will have, to fight with each other and to align in the different levels. And this will actually give the pressure to your star. This is a state of a white dwarf, actually. So when you are a low mass star, at a certain point, you enter these very scary regions where you have this degeneracy, and you cannot go further on in the evolution. You cannot do this nuclear burning easily. So again, mass matters for this reason. If you are a small star like the Sun, you will go through these phases that we will see later. So you will go through the red giant phase. At the end of your evolution, you will become a beautiful planetary nebula. And then you will end up with as a white dwarf, with the core being these degenerate electrons, carbon and oxygen. Now, if you are a massive star, you will go through the red supergiant. You will eventually explode, eventually as a supernova, and the remnant will be either a neutron star or a black hole. This is a movie that was made. So Gaia is a satellite you probably heard of, which is actually looking at the distances of stars in the galaxy. So the idea is to make a 3D vision of the galaxy. And here what you see in this plot is that these are stars. This is the number of stars that you have, and which have different colors. And because we know very well their distances, we are able to determine their luminosity. And you see that the stars, when you do that, you plot them. So this is the luminosity here, and this is the color here. And you see that the stars that were taken randomly, actually, they align through this beautiful diagram. So again, luminosity versus color. And color means temperature. So remember, if you are red, you are cool, and if you are blue, you are hot. Okay, so you go from cool stars to hot stars, and you go actually from low mass stars to massive stars. So this is one of the most important diagrams for stellar astrophysics. It's called the Airspring-Russell diagram. So here you have again the luminosity, the color, and here you have the effective temperature. So you go again to hotter temperature on the left. And you see that if you take stars randomly, they align beautifully in different places of the diagram. They are not randomly put in this diagram. They are really aligned in different phases. So what you see is that there is this beautiful here line, which we saw before in the movie, which is called the main sequence. And this is actually the line where we have this relationship between luminosity and mass, with the exponent 3.5. And you see, this is the time actually where the stars are spending most of their life. Why we see them here? It's just because they spent most of their time here. 90% of their life they will spend on this main sequence. And this is this central hydrogen burning phase. Okay? And then eventually they will move to other places in the diagram. So if I'm the Sun here, I will move here, come back here, and then go whoops, like this. So here you have also an accumulation of stars. It's because this is the second phase of nuclear burning. This is what we call the clumps. This is when the stars are actually burning helium at the center. And then you will move to other places and eventually become a white dwarf here. Okay? So now we will see why the stars are going to move in this area. But remember that a star in this diagram stays there for 90% of its life and then starts to get around. Not in a stochastic way. It goes in this diagram with a very specific way. So the stars burn hydrogen for most of their life. Then they are going to contract again, burn something else, and move around in this HR diagram. Change colors, change size, etc. That's funny. Huh? And then, of course, they die. The first part, you already heard about that. Actually, I'm talking a lot about this hydrogen burning. So this happens through different ways. So it's just making an helium out of 4 protons, but you can do it different ways. So in cool stars like the Sun, so stars with masses below a certain value, let's say 1.2, you actually do it this way. You actually take first 2 protons, and you make a deuterium. This deuterium eventually capture a proton, make helium-3. And if you have 2 helium-3 around, then you can make an helium-4. And if you count, and you're going to release 2 protons. So if you count, you put 6 protons, and actually you get 2 protons out, and you get 1 helium-4. And you can go through different phases. The helium-3 can eventually go capture an helium-4 and then make beryllium, lithium, and at the end of the day, we'll make an helium. Okay, I'm not entering the details, but that's more or less what stars do. And in the case of the Sun, it goes through this path. 70% of the nuclear reactions go through this path, and then the rest goes in this direction. But the net result is the same as Bethe had computed. So you take 4 protons, you make 1 helium, you release actually neutrinos, which was very important also, neutrinos. You know the story that the neutrinos, solar neutrinos were lacking. I will show you something about that if I have time at the end of my lecture. So neutrinos, by counting the neutrinos, it also tells you the temperature. It's another way to determine the temperature at the center of the Sun, because depending on the path you actually go, you will get neutrinos from different paths, and that will tell you, that will quantify the temperature. Okay, that will tell you which reaction is favorite and what is the temperature inside the Sun. Now, if you are a more massive star, you can do it through what is called the Cno cycle. So this is 4 stars that have temperature inside above 20 million K. And the idea is that now if you have some carbon, nitrogen, and oxygen when the star is born, these elements are going to capture protons. And at the end of the day, they will actually make, I won't enter too much into the details, but what you do is that, for example, you start from carbon-12, you capture 1 proton, and you go through this process here. And if you count, actually, you have 4 protons ending in one helium. And again, this is the same net result. The energy that you get from fusing 4 protons is this quantity that we had before. So here in this small movie, you can see on the right the evolution, a model of a star which is evolving on the main sequence. So this is a 1 solar mass star. So this is luminosity as a function of effective temperature. You remember the A-share diagram where we had the stars aligning here. And you see that this 1 solar mass star actually evolves a little bit in this main sequence. So it really stays around here. And this is here on the left, you can see the profile of hydrogen. So you start with something which is flat, the initial abundance. And as time goes, you actually deplete hydrogen at the center. And at the same time, you produce helium. So helium is in green, and you make helium at the center. Okay? So at the end of this phase, you end up with a helium core. Okay? But of course, helium requires higher temperature to fuse with itself. So you need something like 10 to the 8 Kelvin. So in between the 2 phases, the core has to contract. And again, you have this phase of contraction that we were mentioning before. And if you are not massive enough to contract and reach this temperature, then you will finish as an helium white dwarf. But very long in the future, because these stars, they are very low masses and they are not at that stage yet. Okay? But in the very far future, people will find some helium white dwarf star. Okay, so what is interesting is that to do that, you actually have the possibility to fuse 2 helium. You go through beryllium, which is unstable, and you get another helium-4, and you make carbon. So the most abundant element that you will form is carbon-12. But this carbon-12, depending again on the temperature at the center of the star, so the more massive the star, the hotter it is, and in that case, this carbon-12 can also capture alpha particle and form oxygen-16. And here you have a list of other reactions that can happen. So at the end of helium burning, you have carbon and oxygen. And if you are a low mass star, you will stop here and you will become a carbon-oxygen white dwarf. What is very important at that phase is that, so here you see the star, and at the very, very center, so it's really a very compact core, you have the core which is burning helium, and around that, because the surroundings have contracted too, so the surroundings where there was still some hydrogen, the surroundings are also contracting, hotting, and around the core, the helium burning core, you have a shell of hydrogen burning. Okay, so you have fusion in the core, helium fusion, and around you have hydrogen burning shell. And it's very important because in that case you have a very different structure of the star. This hydrogen fusion releases a lot of energy, which implies the star to inflate actually. So you have a very dense core which is contracting, and the star, because of this fusion in a very thin shell, is going to expand. So you have a red giant star, cool at the surface, but inside you have this fusion. And this is where the star starts to move to the red part of the HDR diagram. So here you have the comparison. So this is the lifetime as a function of initial mass of the star for hydrogen burning, and here for helium burning. And you see that there is more than one order of, there are one order of magnitude difference between the hydrogen burning and the helium burning phase. We could say this is the end of the story for a low mass star, because this star is going to enter into the degeneracy regime, and it will become a white dwarf. And that's it. These poor low mass stars, they produce nothing else. But that's not true, actually. The low mass stars, they produce most of the heavy elements later in their evolution. And how can that be? So how can that be? When the star has finished to burn helium, it has a carbon and oxygen core. Okay? This core is degenerate, electronic degeneracy, which actually counterbalance the effect of gravity. And this core is contracting, and around it, the other regions where nuclear fusion has not occurred are also contracting and heating. So the star has actually two shells, a helium burning shell and a hydrogen burning shell. And you can see here, so this is a comparison. So the core, which you see here, is really, really very tiny. Here you have the size of the star. It can reach 500 times the radius of the sun, while the core itself is only 1/10 of the radius of the sun. And what is very important, and I don't think I will go into too much details, is that in this phase, you have this thing which is happening. So here, this is what we call a Kippenan diagram. So this is the center of the star would be here. The surface would be very far away. And here we are just looking to this outside the carbon-oxygen core, which is this small thing that we were having here. And then we are looking at this region. So outside the carbon-oxygen core, you have this helium burning shell. And here you have the hydrogen burning shell. And what happens very regularly is that these two shells are going to contract. And because the helium burning is actually extremely dependent on the temperature, the energy is related to the temperature with a power of 40. From time to time, you will have a flash that will occur to release this energy. So you have a runaway of nuclear reactions, helium nuclear reactions, which will lead to the development of a region which will go and extinguish the hydrogen burning shell. You will have a mixture of different elements. So in the hydrogen burning shell, you burn hydrogen as we have described before. And in the helium burning shell, you produce carbon and oxygen. But when you have the helium flash, actually, you mix the products of this shell with the products of this one, and you engulf, in particular, a lot of nitrogen, which was produced by a hydrogen burning shell. And this nitrogen can capture alpha particle. It's very hot. You can do these things. And then you're going to produce neon-22. Another thing which is interesting is that this neon-22 is going to capture also alpha particles and release some neutrons. You can do the same with carbon-13. You capture an alpha particle, you also release a neutron. And so your star at that time will be full of neutrons. And neutrons, they don't have to go through the nuclear barrier. Actually, they can enter the nucleus, depending on their speed, actually. But you have a large flux of neutrons, which will actually be captured by the iron peak elements. And this is where stars actually make these heavy elements through this neutron capture. At the end of their life, at the end of its life, the sun, when it will go through this phase, will actually produce a lot of neutrons and will produce many of these heavy elements. And actually, the carbon and the oxygen that it has produced will stay in the white dwarf forever. So it's lost for the enrichment of the galaxy. But it's really through this phase that the stars will really contaminate their surrounding. And this is where I show you again this plot. You remember this technetium spectrum. So this is when technetium is actually made, really at that phase. And it's an unstable element. And you see here, it's the same kind of star. You have barium, which is a heavy element too. And this is really through this phase that low-mass stars actually produce these heavy elements. Also, these low-mass stars, they have a lot, they are huge at that phase. They are red, they are huge, the atmosphere is cool. You have these strong pulses which go through, and you have a lot of stuff going on in the atmosphere. And through these shocks, you will be able actually to launch very strong winds. So here you can see in this beautiful image, actually, you can see the white dwarf is here. And you see these circles, actually, which are probably related to these different pulses that the star has undergone inside, which have launched this very strong wind. And you see this is at that phase that actually you lose a lot of material. And here we can count the last pulse occurred 18,000 years ago, and it lasted for 200 years. And this is more or less what we find in the models, depending on the mass of the star. And you can even see it live. You can even see some changes in the wind or in the surroundings of this kind of stars by looking at different times. And here you see this is one of these famous AGB, and you can see it's observed at different times, and you see the envelope is actually changing with time. And you can quantify the amount of material which is lost at that phase. It's huge, actually, 10 to the minus 4 solar masses per year. You may know that the solar wind, the sun, loses 10 to the minus 14 solar mass per year presently. So it's 10 orders of magnitude higher. And this is also one of these beautiful planetary nebulae where you can see here the traces of these pulses. And here you see the planetary nebulae at the end, the ejection through jets, etc., at the end of the evolution. So here in yellow, you can see these low mass stars. So what we call low mass star is below 8 solar masses. If you are below roughly 8 solar masses, you will never go through something more exciting than helium burning at the center and these pulses, which is already quite exciting, I would say. And here in yellow, you can see the elements and the fraction of these elements, estimated fraction, which is produced during these phases. And you see that you populate this part of the diagram, so you produce, through neutron capture, you produce these heavy elements in these low mass stars. Okay, this is it if you are a single star, and after the break, you can see what happens if you are a double or in a binary. And I thank you for your attention for this part.